All right. So once again, we do have several bone markings on these things that we do need to find. Remember that oftentimes they're going to either be named off of what's passing through them in the case of the carotid canal. Anyone want to guess what's going to pass through the carotid canal? The carotid artery. Fairly important, as is the jugular vein. Okay, so these are two big ones. So this is also our foramen magnum here. Remember that when it comes to learning these structures, I would really, really, really recommend learning where the structures are. Okay, don't just say, okay, I'm going to learn the structures on the bottom and go, okay, foramen magnum, jugular foramen, carotid canal, and so on and so on and so on, because that's going to get you confused a little bit. Learn the carotid canal as this hole right here that is just kind of medial to this bony protrusion. You want to remember what this bony protrusion is? Looks like you're going to sign on a credit card machine with a stylus. What do we call bony protrusions now? Like long, pokey, bony protrusions? Internet people, y'all can answer this too. Anybody? Oh, look, I put something up here that isn't labeled, and all of a sudden y'all don't answer it. All right, what is it? Come on. Styloid, what? It is the styloid, but is the styloid what? Styloid's the first word. What's the second word? Now we just need to describe the structure. Process. Very good. It is the styloid process. Okay. This one back here is our mastoid process. So we're going to have muscles for talking and speech, or those are the same thing, breathing, stuff like that attached here to the styloid process. We're going to have muscles that actually allow us to move our head and neck attached right here on the mastoid process. So those are going to be very important structures as well. We can see our sphenoid bone. We see the sella turcica, which is basically this little cavity that's going to support the pituitary gland. That's this one that looks like a bat, also called the keystone bone of the skull sometimes. Here we have the ethmoid bone. Ethmoid bone has this ridge down the middle of it that we call the crista galli, and then we have a bunch of little holes. The holes are what we're going to call the cribiform foramina, where they're going to form what's called the cribiform plate. This is where we're actually going to pass our olfactory nerves through these. That's why those are important. All right, this brings us to the hyoid bone. Now, underneath the jaw, kind of posterior to the jaw, you're going to find a little bone back here just above your voice box. That little bone just above your voice box is going to be the hyoid bone. The hyoid bone is unique because this is the only bone that we have that does not directly articulate with any other bone. Okay, this is it. Okay, all of your other bones will articulate with at least one other bone, with the exception of the hyoid bone. It is just floating in space. It is floating in space, and it is held in place by a whole bunch of different ligaments and tendons. Okay. Importantly, these ligaments and tendons are going to either connect this bone to other bones in the case of the ligaments, but the tendons that connect to these are going to be attached to muscles. The muscles that are going to attach to these are going to use this to move the hyoid bone in or out, up or down, so that we can do things like swallow and talk and pressurize the air that we move through our vocal cords. Okay. All of that stuff is going to move through that hyoid bone. Okay. All right. Now, the fetal skull looks a little different than the adult skull, mostly because it looks like a little alien that's moderately creepy. You want it to look more alien-like? Look at it even earlier in development. Now, the reason it looks a little weird is because we have a massive brain case. And the thing is, this is actually going to get worse over time. So we're actually going to see this brain case grow faster, even than the facial bones and stuff down here during the first couple of years of life. That's just because our brains need to grow really, 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 really fast. Okay. Now, it's very important that we have room for our brain to go really fast because we are learning a lot within those first couple of years. We learn things like to talk or to walk and to talk and to recognize speech and all of those kinds of things. Okay. However, we also need to make sure that we don't have this giant structure that is super rigid, that is protecting a whole bunch of soft, squishy stuff that controls everything, passing through a hole that is slightly smaller than it is through the birth canal. Because that would be a problem, right? That would be a problem for the mother because it just simply wouldn't be able to pass. And the only way to pass it would be to break it. Well, that would be bad for the fetus. It would also be really, really bad for the mother as well. Okay. And in the past, that is actually one of the ways that people would die in childbirth, is that literally the baby's head would get stuck in the birth canal and they would both die. If that sounds awful and gruesome, it is. Okay. Really, 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 really bad. So we have to give points of flexion. We get those points of flexion here in these fontanelles. The sutures are not closed, and we're going to have these big soft spots here. This basically makes that your skull structure somewhat malleable so that it's easier for it to pass through the birth canal. But also so that as the brain grows, these things aren't fused together, so these bones can continue growing out along with the brain as it is growing. All right, now, all of the brain stuff is actually going to be connected to a bunch of nerves. This way we can get nervous information out of the brain so that we can tell stuff what to do, but also so we can get sensory information from all of these places into the brain so that it can be looked at, okay? Now, to be able to do this, we need to protect your spinal cord. Now, to understand this, you need to realize that your spinal cord is nothing but a bundle of nerves that are going to be inside these bones. So there's going to be a little cavity about the size of your little finger that is going to pass all the way through these bones. One of their primary jobs, or one of the primary jobs of the vertebral column, is going to be to protect that spinal cord. We need to have a big shield around it so that random things cannot touch or interfere with our spinal cord functions, okay? Now, the next thing that we need to be able to do here is that we also need to allow motion and allow movement of the spinal cord while still making sure that it's protected, okay? That means these bones can't just be static shields. They also have to have some amount of flexibility between them in order to allow that motion to happen. Now, as you look at this, you're going to see that we have 5 major regions labeled here. We have cervical, thoracic, lumbar, sacral, and then finally coccygeal vertebrae. In this, we have 4 different curves. We have a curve here in the neck. We have a curve here in the back, another backwards curve here in the lower back, and then finally another frontwards curve here in the sacrum. Now, importantly here, 2 of these are present at birth. The thoracic curvature and the sacral curvature are present at birth. You basically, when you're born, you have a spine that it's that's going to look like this. And if you drew the rest of it in, you'd have a head, arms, and then your legs and stuff would be wrapped around here, which we would tend to call a fetal position, right? Okay, so your spine is actually going to help you hold that fetal position when you're born. However, we have a couple of very important kind of developmental stages that are going to occur that are going to fix the other 2 curvatures in place. So to fix the cervical curvature and the lumbar curvature in place. So what do you think is going to happen or be happening when we are developing our cervical curvature? So we're no longer going to be shaped in this C. We're instead going to have a little bit of a C shape through the back, and then we're going to flip that up here. Well, isn't our head right here? So what did we just learn how to do? Learning how to hold our head up. You develop that cervical curvature whenever you learn how to hold up your head, okay? That is why that is a very important part of development of the baby. Like they're doing this at 6-8 months or something like that typically, maybe a little earlier, okay? That is them learning to hold up their head is important because this is actually developing that spinal curvature. Now we are positioning the weight of the head on top of the spine so that we can now move the spine forward. Now, what do you think we're going to do to cause the next curvature to develop, the lumbar curvature? When do you think that happens? Not quite crawling, standing, okay? When you go to stand, that's to say you go from positioning all of your weight kind of straight down onto your limbs and you bring that weight up. In order to bring that weight up, we have to fold our lower back up to reposition the weight. Now we can position all of that weight vertically. Whenever you are learning to stand, whenever you are learning to walk, you are developing that lumbar curvature. The reason that process can take so long is because you are having to develop that shape in the bones themselves. This isn't just a musculature thing. This is, we are literally changing the shape of the bones as they are growing as well, okay? But all of that is there to position our weight onto or straight up and down so that we can now position or move our weight out to our hips so that we can walk, okay? Now, that's very important because we are bipedal. We walk on two legs. This kind of frees our arms. Now, we can also see as we move down through each region of the bones, what else do you see happening to the bones? What's happening? How so, though? Ex- exact. They're getting bigger. Like these bones are very, very thin. Like you said, they're stacked really, really closely together. Here, it seems like they're spreading further apart. They're getting a little bit further apart in between the bones. Yes, because we're getting bigger cartilage pads, but also the bones themselves are getting quite a lot larger. Why? Why do you think the bones are getting bigger? Support more weight. Exactly. As you move down, these bones have to be able to support more weight. Thus, they have to get bigger. That's why the bones in the lower back now that are supporting basically everything from your head down, these bones have to be quite large. And then we get into the sacrum where these bones get even larger to the point where we actually have them fused together. So instead of them acting like a single bone, or sorry, instead of them acting like 5 individual bones, they're now going to act as a single bone and be as strong as we can possibly make it. This is also where we're going to take all of that weight and push it out to the hip. So we have to have big, strong attachment sites for the hip bones here. Then we get to the coccyx. Coccyx is tiny, 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 tiny. This is anywhere from 3 to 5 vertebrae that are fused together. And that variance is because of genetics. Okay. However, they are fused together for strength. When you're first born, they're actually not fused together. That process takes a while. This is actually one of the things they can do to age skeletons by looking at how fused together the coccygeal bones are. This is your tail, or at least this is the remnants of your tail. We have this few number of vertebrae, so now all of a sudden we don't have a visible tail from behind. Because of that, there's no more selection on it to get rid of it. It's really just there. This is once again kind of a vestigial structure, at least in part. We do actually have some muscles and things like that that are going to use it as an attachment site, though. All right. If we look at a regular vertebrae, we're going to see one primary hole. This hole here is going to be the vertebral foramen. Once again, foramen means hole. So this is a hole for the spinal cord, which remember is about the size of your pinky. Now, we have a couple of bony protrusions. These bony protrusions, remember, are processes. This one points out the back, so we're going to call this the spinous process. So this is posterior back here. Okay, so if you run your knuckles up and down your spine, those bumps you feel are actually going to be the spinous processes of your vertebrae. Now, these are going out to the side. So the plane that goes out to the side and cuts something into cross sections, remember, was the transverse plane. So these are going out to the side. So these are going to be transverse processes. Now, this structure right here on the other side of the hole is going to be called the body. Okay. The body here is going to change shape and is going to change size depending on where you are in the vertebral column. The lower you are, the more weight you're holding. Thus, we need to have a larger body to be able to support that mass. We're also going to have much larger pads as we move down to support additional force and thus support additional shock. Okay. Now you're also going to see a couple of little structures poking both up and down. So you are looking at the top of this bone. Okay. So these 2 points right here basically pointing up at you. These are going to be articular processes. In this case, they're on the top. So they're superior articular processes. And they have a little divot on there. That's basically going to allow them to interact with the vertebrae that is above them. This is the way that those 2 vertebrae can move among or between each other and allow you to kind of move your spine anterior or posterior. Okay, so you can see something like this, where the chin of one kind of meets with the top of the other. And we're going to have these big holes on the sides of the vertebrae that we're going to call intervertebral foramen. So intervertebral means in between the vertebrae. Just like an interstate is a road that goes between states, the intervertebral foramen is a hole in between the vertebrae. This is where we're going to have spinal nerves come out of these. So these are going to be very, very important as well. All right. Now, to tell the different vertebrae apart, we have, like I said, 3 different types that we're going to need to tell apart. Cervical vertebrae. We have 7 cervical vertebrae. This is actually going to be conserved throughout almost all mammals, including something like a giraffe. Still just has 7 vertebrae. They're huge. They're like literally 1.5 feet long or 2 feet long in some cases. They're massive. However, still just 7. Okay. In us, our heads are fairly small. Thus, these bones are going to be small and light. Okay. They're only supporting the weight of the head and neck. okay? Now, the easiest distinguishing characteristic for a cervical vertebrae, other than the fact that they're small and light, is going to be that we have 2 extra holes. In addition to our vertebral foramen here, we actually have 2 others. These are also going out to the side. So what do you think we're going to call these holes? They're going out to the sides. What did we call the plane that goes out to the sides? Transverse, perfect. So these are going to be our transverse foramen. So cervical vertebrae easily identified because they have 1, 2, 3 holes. Cervical vertebrae have 1, 2, 3 holes. That is how we're going to identify any cervical vertebrae. Now we have 2 special cervical vertebrae. The 2 special cervical vertebrae that we have, hold on, let me fix this because that is annoying. All right, so this is our first cervical vertebrae. So whenever we are looking at vertebrae, we're going to number them from top to bottom. So the very first cervical vertebrae is going to be C1. This one has a special name. It is Atlas. If you know your Greek mythology, you know that Atlas was the Titan that was cursed by the gods to hold the weight of the world on his shoulders. If you've seen the cover of Atlas Shrugged by Ayn Rand, it's that person holding the globe on their shoulders. Okay, this bone is named that because it holds the weight of your world on its shoulders. This is the bone that is going to support the weight of the head. Okay, because of that, it is incredibly, incredibly important. Okay, now it's going to have these couple of superior articular facets that are going to articulate with the occipital condyles on the occipital bone of the skull. So this connection between the occipital condyles of the skull is going to the occipital condyles, remember, we're kind of rough and rounded. They're going to sit in this little facet, which is basically concave. And that interaction is going to allow you to nod your head. Okay. So the motion of nodding your head is because of the articulation between the occipital condyles of the skull with the superior articular facets of Atlas. Okay. Now we also have this big divot right here. This big divot right here is actually a facet for the second cervical vertebrae. The second cervical vertebrae is axis. Okay. So axis is named this because this is going to be the axis around which your head turns. Okay. So axis has this little structure on it called the dens. Okay. So it's this right here. So it looks like a little tooth, thus dens, like dentist. Okay. This structure points up because it's going to fit in that little facet on Atlas. And then as you go to turn your head, all you're going to be doing is you're going to be rotating Atlas on top of axis, on top of these superior articular facets of axis, and they're going to rotate around dens. Okay. Axis, importantly, is going to stay in place. The second cervical vertebrae here will not move. Okay. So when you are turning your head, the second cervical vertebrae does not move. When you are nodding your head, the first vertebrae does not move, which means these bones are going to be much, much more static than you would think they are. Okay. Whenever you're turning your head, Atlas is going to spin around this dens structure here, and it's going to move. Axis itself is going to stay place. This way we can keep everything nice and even and position all the weight and stuff down through our neck and distribute it evenly. Okay. All right. Those were 2 special cervical vertebrae. However, they still have 1, 2, 3 holes. So they still have the 3-hole cervical vertebrae identification. All right. Thoracic vertebrae. We have long inferiorly pointing spinous processes. We have transverse processes that kind of point posteriorly with a bit of an arc rather than being kind of flat. We also have a roughly triangular shaped body and a triangularly shaped vertebral foramen. Okay. Or actually, I guess more of a roundish shaped vertebral foramen. We also have special little facets on these. So this little divots on the bodies of the vertebrae. This is actually going to be where the ribs are going to attach. This is not something we're going to find on any other sets of vertebrae, only on the thoracic vertebrae. That's because our ribs attach here, and that's what makes them thoracic vertebrae, because they form our thoracic cage. This is easier though. They look like giraffes. Long pointy nose, check. Inquisitive ears, looking at you, reaching for sound, all the way down to adorable little horns on top. Okay. If you look at a vertebrae, looks like a giraffe. It's going to be your thoracic vertebrae. Now, lumbar vertebrae, big, heavy. Notice the body here is much, 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 much larger. We have a flattened vertebral foramen, so now we're definitely triangular in shape. We have big, heavy articular processes, both superior and inferior articular processes are very heavy, and our spinous process now basically points straight out the back, okay? Also very, very heavy. This is a moose. Big schnoz, pointing straight out, big schnoz. Beard, beard. Horns, horns. Big body, big body. It's a moose. Does it look like a giraffe? It's a thoracic vertebrae. Does it look like a moose? It is a lumbar vertebrae. Is that silly? Yes, but now will it make it easier to remember? Probably, or at least I hope so. All right, coccygeal vertebrae, sacrum and coccyx. Once again, 5 vertebrae that are fused. These completely fuse around the age of 25, 30, somewhere around in there. They also form the wall of our pelvic cavity. That means we have to have a nice smooth surface in here because we have a bunch of soft squishy bits in here, okay? We also have these ear-shaped structures on the outside that we're going to call alae, or the auricular surface, which is actually going to be where we're going to stick the hip bones onto these. Then we're going to have some holes in between our sacral vertebrae that we're going to call sacral foramina. These are important passageways for nerves. Then we have the coccyx, which we've already talked about there. All right, then we have the thoracic cage. Thoracic cage is composed of the ribs, the thoracic vertebrae, and the sternum, as well as the cartilages that connect all these. Now, we have 3 major divisions of ribs. We have true ribs and false ribs. And then within the false ribs, we further divide those into false ribs and floating ribs. The floating ribs are so named because they don't articulate with or attach to the sternum at all, okay? The true ribs all attach to the sternum through their own costal cartilages. So this is rib pairs 1 through 7. So 1, 2, 3, 4, 5, 6, 7. All of these attach directly to the sternum through their own articular cartilages. Rib pairs 8, 9, and 10 attach through the costal cartilage of rib pair number 7. So they don't attach on their own, okay? So because of that, these are false ribs. Rib pairs 11 and 12 don't attach at all, but they do kind of cover things like the top of your kidneys and stuff like that, okay? Now, anteriorly, we do have the sternum in this kind of sternal region, okay? The sternum is composed of 3 different bones. We have the manubrium, then we have the body, which is this bit here, and then we have the xiphoid process. The xiphoid process is yet another structure that is going to ossify over time, okay? However, the ribs, thoracic vertebrae, and the sternum, these are all going to be incredibly important sites for muscle attachment, okay? Whether that is muscle attachments for things like big, heavy muscle movements, for like moving our bodies around, or for muscles for breathing. These are going to be very important sites for muscle attachment. They're also going to be important sites for understanding where other things are placed. So oftentimes we will actually talk about where parts of the heart are placed based off of the locations of the ribs, or at least the spaces between the ribs. Like you're going to listen for particular heart sounds in between particular rib pairs. All right, ribs are fairly straightforward. We have kind of a head, neck, and then we have a couple of little bumps here, which is basically going to be where they're going to articulate with the ears of our giraffes, okay? And then we're going to have a little bit of a flat spot on the end, which is where it attaches to the costal cartilage. All right, I think that's it there. You have your structure list for the things that you need to know on the axial skeleton. So I'll give y'all a few minutes to look at those things, and then we will get started on the appendicular skeleton. So say 15 minutes to work on this, and then we'll take a break from looking at stuff, and then we'll talk about the appendicular skeleton. Sound good? All right, let's get to it. Also, there's nothing to say that right now wouldn't be a great time to also continue studying stuff on the skull, but that's completely up to y'all.